Hi, Assalamualaikum and a very good morning. So now we are in chapter 5, the states of matter. And now we're going to focus on the subtopic of 5.1 gas, part 3 of the video. So in this video, we're going to learn on how to define and perform the calculation using Dalton's law. Next, we're going to explain the ideal and the non-ideal behavior, or known as the real gases, in terms of the intermolecular forces as well as the molecular volume. Next, we're going to explain the condition at which real gases approach the ideal behavior. So, without any further ado, let us start with part 3 of the video first. So, Dalton's law of partial pressure. So, Dalton's law of partial pressure stated that the total pressure of a mixture of the non-reacting ideal gases at a constant temperature is the sum of the partial pressures exerted by each of the constituent gases in the mixture. What is meant by this was the total pressure is the sum of the partial pressure of each component of gases in the container. So let's say if we have component A, gas B, as well as gas C, then the total pressure gonna be PT is equal to PA plus PB plus C. If we have another gases which is gas D, then we can add up with PD here. So now let us focus on this diagram first, which is only gas A and gas B. So for the writing of the partial pressure, we know that our ideal gas equation goes with PV is equal to nRT. So if we want to find a partial pressure of A, then we can bring the V term on the right hand side. So it's going to become nRT over V. And if we were to specify it for gas A, then we can put PA here and the number of mole of A. So similar goes to the another component which is gas B here. So it's going to be PB is equal to nRT over V. And this equation here can be summed together, which is PA plus PB is equal to NART over V plus NBRT over V. And Na plus Nb, which is here and here, which is the sum of the number of mole of both of the component equals to the total number of mole. So when we add together, then we can get NT here. And this shows that PV is equal to nRT, in which when we are talking about the total pressure, then the number of mole here are going to be the total number of mole of each component in the container. And similarly, we can use the mole fraction in order to get the ratio of the components. So let's say if you have a mole fraction of A, so it is equal to the number of mole of component A divided by the total number of component present inside the container. And the number of mole here, it is directly proportional to the pressure. So you can also use Na over Nt or Pa over Pt because they are directly proportional when we write them together. So PAV is equal to Na over Rt. And then if you were to divide that with a component of PB, NB over RT, you can see that RT and RT can be cancelled out, volume and volume of the container can be cancelled out, and therefore they are directly proportional. And that is why you can use either Na or the pressure in order to figure out the mole fraction. And of course, if we were to find the partial pressure of each component, as mentioned, we can also use PA, because you know that XA is equal to PA over PT, right? So if you want to find the partial pressure of A, then PA is equal to the mole fraction multiplied by the total pressures that are in the container. Now we're going to look into the example. So a sample of gas at 5.88 atm contains 1.20 gram of CH4, which is the methane, 0.4 gram of hydrogen gas, H2, and 0.10 gram of helium. So you can imagine that inside a container, they're going to be consisting of three gases. So we have our CH4 gases, and then we have our hydrogen gas as well as helium. And these will have their on masses, which is 1.2, 0.4, as well as 0.10 gram. And then the total pressure inside the container going to be 5.88 atm. And then for question A, we need to find out the partial pressure of each component, which is the CH4, the hydrogen, as well as the helium in the mixture. So in order to do that, we know that PA is equal to XA multiplied by PT, which is our total pressure here. And since we need to specify for the gases that we have, so we can do PCH4 is equal to XCH4 divided by multiplied by PT. And then we know that the XH4 is equal to the number of mole of the CH4 divided by total number of the component or the number of mole of each gases, and then multiply by the total pressure. Okay, and we're going to repeat that for hydrogen and helium inside the mixture. So the first thing first, we need to find the number of mole of each component of gases first. So the number of mole of the CH4 is equal to mass divided by the molar mass, in which the mass of the CH4 is 1.2 divided by the molar mass, which is 12 plus 4 multiplied by 1. So we have 16. So 1.2 divided by 16 going to be 0.075 mole. And then we're going to find the number of mole of the hydrogen, which is mass divided by the molar mass, which is 0.4 divided by 2 gram per mole. So gram and gram going to be cancelled out, and then we're going to get the mole of the hydrogen going to be 0.2 mole. And then we're going to find the number of mole of the helium, where the mass of the helium is 0.1, and the molar mass going to be 4.0 gram per mole. So similarly, once we do the maths, we're going to get 0.025 mole. And then we can find the total number of the number of mole of each component in the gas in the container, in which NT is equal to 0.05 plus 0.2 plus 0.25, in which we have the total number of mole to be 0.3 mole. Okay, and now we can find the partial pressure of each component. Let us start with the partial pressure of the methane first. So we have PCH4 is equal to X, the mole fraction of CH4 multiplied by the total pressure, which is 5.88. As mentioned, we have the number of mole of CH4, which is 0.075 mole, and then the total number of mole we have known it to be 0.3. So mole and mole can be cancelled out, and then once we do the maths here, we're gonna get 1.47 atm for the partial pressure of the methane gas. And then we're going to repeat that for the hydrogen gas. So the mole fraction of the hydrogen multiplied by the total pressure. So the number of mole of the hydrogen divided by the total number of mole in the container. So the number of mole of hydrogen is 0.2, and then the total number of mole here is going to be 0.3. So mole and mole going to be cancelled out, and then once we do the maths here, we're going to get 3.92 atm. And lastly, we need to find the partial pressure of helium, in which the mole fraction of the helium multiplied by the total pressure. So 0.025 mole divided by 0.3 mole multiplied by 5.88 atm. So mole and mole can be cancelled out, and then once you do the maths here, you're going to get 0.49 atm. Okay, and this is how we find the partial pressure of each component one by one. And then you can double check your answer, because you know that PT is equal to PA plus PB plus PC, right? So because you have three gases, so PA here refers to the CH4, so you can say that 1.47 plus your partial pressure of gas B, which is 3.92, plus partial pressure of gas C, which is 0.49. So when you add up all together, what you're going to get is 5.88 atm. So you know that your answer is correct, because the Dalton's law of partial pressure stated that it is equal to the sum of partial pressure of each component. Okay, and now we're going to focus on question B. So question B stated that what is the partial pressure of the CH4 and the hydrogen gas if the helium is being removed? So what's going to happen to this one and that one? So if the helium is being removed, basically there's nothing happen to the CH4 and H2. The partial pressure of the CH4 and the hydrogen will still remain the same. And because of that, the partial pressure of CH4 going to be 1.47, the same as usual, and the partial pressure of hydrogen is 3.92, the same as before. What changes is the total pressure. So the total pressure will only left 1.47 plus 3.92 atm. So this is what left in the total pressure. But each component is not affected by the others. All right. Now we're going to look into the application of the Dalton's law. So during the reaction or during the experiment, some of the air can be passes through the water and the gases will be collected over the container by using the water displacement method. So let's say the air that is produced from the experiment is oxygen. So you know that the total pressure here will include the partial pressure of the oxygen from the experiment that passes through here, as well as the partial pressure of the water vapor. The water vapor came from the water itself, in which the water here can evaporate at any time at any pressure. So you have to include that the water vapor will also contribute to the total pressure here. And that is why it was stated here is that the total pressure is not only from the particular gas from the experiment, but also includes the water vapor when we use the water displacement method. So to understand more about this, let us look into the example. So consider the reaction below. Let's say we have our potassium chlorate in which it is heated. So when it is heated, it will produce KCl, and then the byproduct of the reaction going to be oxygen gas. So it's going to be passes through the water, and then it was collected over the container here. And as what you can see here, we have our partial pressure of oxygen as well as the partial pressure of the water vapor, in which the water itself gonna evaporate and collected up to the container here. So we have to consider both of these in order to answer the question. So it was stated here is that a sample of 5.5 liter of oxygen gas is collected over water. So the volume of oxygen that we obtain is 5.45 liter. And the total pressure here, PT, is 735.5 torr. And it happens at a reaction of 25 degrees Celsius, in which we need to convert that into Kelvin, where we're going to get 298.15 Kelvin when we add up with 273.15. So we need to figure out how many grams of oxygen have been collected. So we need to find out the mass of the oxygen gas. So in order to find out the mass, we can find the number of mole first. Okay, and it was also stated here is that the vapor pressure, which is the partial pressure of water, is given as to be 23.8 torr, which is the water vapor. So we can write down all the information that we have to be like this. And now we need to find the partial pressure of the oxygen first. So we know that PT is equal to PO2 plus PH2O, which is like this. And then we need to find the PO2 first. So we have our PT here to be 735.5 torr. And then our partial pressure of water vapor is 23.8 torr. So the partial pressure of oxygen we're going to get is 711.7 torr. And this torr here can also be changed into ATM, because we know that 1 ATM is equal to 760 torr. So let's say if we have 711.7 torr, then we can find the X ATM by doing a cross multiplication. So we're going to get the unit of ATM to be 0.936 ATM. And from here, when you get your pressure here, and you already have your volume, and then you have your temperature, what you can find here is that you can use the PV is equal to nRT, which is your ideal gas equation. And we can specify the pressure here to be the pressure of oxygen, the volume of the oxygen, as well as the number of mole of the oxygen. So we have pressure, volume, temperature, and we need to find the number of mole because R is the gas constant. So we can substitute the value. in which we need to find the number of mole. So the pressure of the oxygen is 0.936 atm, and then the volume going to be 5.45, and then your gas constant is 0.08206 liter atm per mole per Kelvin, and then your temperature happens at room temperature, which is 298.15 Kelvin. So Kelvin and per Kelvin can be cancelled out, and then liter and liter can be cancelled out, atm and atm can be cancelled out. So what's going to left here is the mole. So once you do the maths here, you're going to get your number of mole of oxygen going to be 0.2086 mole. From the mole, you can calculate the grams of the oxygen produced by multiplying the mole, which is 0.208 mole, multiplied by its molar mass. So the molar mass of oxygen is O2, right? So it's going to be 2 times 16, which is 32. So 0.2086 multiplied by 32. And lastly, we're going to get the mass of oxygen to be 6.75 gram. And this is how you apply the Dalton's law in order to solve the question. Next, we're going to see the deviation from the ideal behavior. So before this, we have talked about the ideal gas behavior, we have talked about the ideal gas equation as well as the gases law. But instead, in reality, the gases that we are having is not ideal, in which means that in real gases, there are forces of attraction between the gases molecule. Yang mana diorang ada daya tarikan, for example, London-London dispersion forces or dipole-dipole forces between them. In ideal gases, we're just going to ignore the intermolecular forces. Okay, and because that in real gases, they're going to be an attractive forces, what you're going to do in order to correct the ideal gas equation into Van der Waals equation is that you're going to add up the term n square A over V square, in which it's going to include the attractive forces. Okay, dekat ideal kita abaikan, dekat real gases kita kena ambil kira attractive forces. And because of that, inside the pressure term here, we need to add up the attractive forces. Okay, so ini adalah ideal gas equation, PV equal to nRT, tetapi sekarang kita kena include. So it's going to be n square A over V square, in which this refers to the attractive forces. And at the same time, in ideal gases, we tend to ignore the volume of the gas particle. Pasal mula-mula kita kata dah, volume of the gas particle is negligible, we can ignore. But instead, in a real gas situation, we have to consider the volume that is occupied by the gas. And for that reason, we need to use the term NB to take into account the volume of the gas molecule. So what will happen here is that at the V term here, we're going to deduct it with our volume that is occupied by the gas molecule, so that we can only find the effective volume. And for the others, which is nRT, we just copy it back. And for this reason, we have created a Van der Waals equation, or known as the real gas equation. Okay? And this situation here happens when we are dealing with the real gases. However, there will be no calculation that's going to be included for our syllabus. It is enough for you to understand that we need to include the term here in order to correct the ideal gas equation. Okay? Now, we're going to see the condition at which the real gases, gas yang berada dalam reality, boleh menjadi seolah-olah ideal. Apakah dua syarat tersebut? So, these two situations includes at low pressure and then at high temperature. So, at low pressure, it means that we have our volume of the container to be very, very high. So, when the volume of the container is very, very high, it means that the gas particle going to be far apart from one another. So, when the gas molecule is far apart from one another, the attractive forces is not there. Okay, seolah-olah macam tiada. And because of that, it gonna adopts the ideal gas behavior, because the intermolecular forces is now become negligible ataupun boleh diabaikan. So, condition yang pertama, at low pressure. For the second situation is at high temperature. So at high temperature, the molecule will move very rapidly because there's going to be an increase in kinetic energy. So when the molecule moves very quickly from one places to another, you can say that the forces of attraction between the molecule can be overcome. Diorang boleh mematahkan daya tarikan tersebut. Seolah-olah there is no forces of attraction between them. And because of this, you can say that the intermolecular forces become negligible and can be ignored. And hence, at this situation, the real gases will almost be like an ideal gases. Okay, because the intermolecular forces dah tiada. Okay, so remember, the condition at which real gases can approach ideal behavior is at LP high T, which is lepak high T, low pressure and high temperature. Okay, so I think that's all for today's video. See you again some other time. Bye!